This is lesson 10.1 and 10.2. So a circle is the set of all points that are equidistant from a point. We call that point the center. So this circle has a center P. We would name the circle by the center. So this would be circle P like this. They use a little circle symbol with the center drawn in it, so we know it's not an O or 0. And circles are congruent if and only if their radii are congruent. So if I could see that segment AC here, which is a radius, which we'll talk about what a radius is, and segment BD is congruent to each other, then these two circles would be congruent. So now for what a radius is, and all the other different segments and lines in a circle. So a chord is any segment where both of the endpoints are on the circle. So this chord right here starts on the circle, ends on the circle. It's a segment, that's a chord. The diameter is another type of chord because we see that there's an endpoint on the circle, an endpoint on the circle. It just so happens that this one goes through the center, so that makes it a diameter. And a radius is any segment from the center to the edge. A secant is a line or segment that touches the circle twice, so it's very much like a chord, right? This portion of it would have been a chord, but as soon as I'm including anything that existed outside of the circle, it becomes a secant. So even if I just went one way and I looked at it like this, that would be a secant because it has parts in and out, but it also touches the circle twice. A tangent is a line or a segment that touches the circle just once, and that point we call the point of tangency. All right, so a tangent line touches the circle exactly once. Where it touches the circle is called the point of tangency. So for our first example, we're going to give an example of each of the items in the diagram. So a tangent line. I see this line touches just once right here. So I can name it by any two of these three letters. So let's call it MN. The center, there's only one center in this picture. That's O. I'm not putting circle O because I'm not naming the circle. I'm naming the center, which is just a point. The secant. Secant is a line or segment that touches the circle twice and has parts both in and out. So if I wanted to do this whole line here to be my secant, I can name it by any two of these three letters. I could name it by the Q and the P, that's fine, so let's name it QP, but because it went in and out and it continued, we're going to use the line symbol. So the symbols are very important with how we mark our segments, lines, rays, whatever they are. The radius. So radius has to go from the center to the edge of the circle. So there's three of them in this picture. Let's just pick one. Let's pick OQ. Let's make sure we're still recording. Okay, because that went away. All right, OQ. The point of tangency was the point where it touched the circle. The tangent line here touched the circle at R. A chord. Remember, a chord is a segment that touches the circle twice. So there are two chords in this picture. I'm going to focus on chord QP because the other chord I can call something else in this picture. So chord QP here, if I don't include the parts that go outside the circle and I just call it a segment instead of a line, that's the difference between our chord and our secant here. And now the diameter. I saved the other chord to be called the diameter because the other chord in our picture went through the center. So RP would be the diameter. So this is one for you to try, pause, answers are posted online. A line is tangent to a circle if and only if the line is perpendicular to a radius at the point of tangency. So if I see that I have a radius and it's perpendicular to a line here, that means that line had to be a tangent line. And the reverse is true. If I know that there's a tangent line there and I connect a radius to it, then I can automatically assume there's a right angle there. So in example 2, we want to determine is segment DE tangent to circle C. So we want to check if there's a right angle at the point of tangency. To do that, we're just going to see if there was a right triangle that we made, right? Because if there's a right triangle, that means there was a right angle. Opposite where the right angle would be is the hypotenuse. So this would be the hypotenuse. This would be my C value. But it doesn't make sense that 2 would represent this whole line. So notice how the 2 is kind of just out here. They didn't give us any sort of brackety thing to show us that it meant the whole thing. So we really need to figure out how long this whole thing is. Since every radius in a circle is the same, if this radius was 3, this radius is also 3. So together, this side is 5. So we're going to check, is 5 squared equal to 3 squared plus 4 squared? And for those of you who have memorized the Pythagorean triples, you might notice that this is in fact 1. But we're still going to show that 25 does in fact equal 25. So yes. Oh, I don't need to write the so. That's silly. Yes. A right triangle has a right angle. Just yes is fine. I just want to give a bit more of an explanation here. But if you just told me yes, as long as you showed me your work, you're okay. So here's try 2. Pause if you'd like. Answers are posted online. For example 3, segment AB is tangent to circle C. Find the radius of the circle. So now we know for a fact it's tangent, so I can add the right angle symbol there, which means this side combined is my hypotenuse. So if I want to combine the 50 and the r, I have to add them together. So I'm going to write it as r plus 50. You could have written it as 50 plus r. That will not make a difference. And we know we could use Pythagorean theorem on all right triangles. So we're going to do r plus 50 squared equals 80 squared plus r squared. We have to be careful with our r plus 50 squared. That's really r plus 50 times r plus 50. And that means we have to distribute or FOIL, depending on how you learn that. Right? Everything in the first set of parentheses goes to the second. So the first thing goes to both, the second thing goes to both. So r times r is r squared. R times 50 is 50r. 50 times r is 50r. And 50 times 50 is 2500. What's really nice here is these r squareds, gonzo. So we are not having to worry about factoring or anything like that to solve. So I really have 100r plus 2500 equals 6400. So now we're going to take 2500 away from both sides, and we get 3900. And when we divide that by our 100, we get r is just 39. So here's try 3. Pause if you'd like. Answers are posted online. Next, we have the ice cream cone theorem. Two tangents from a common external point are congruent. So if I have two different tangent lines that meet, the two segments will be the same. And I call it the ice cream cone theorem. That's not its real name, because I imagine this looks like an ice cream cone. And if you wanted to put a scoop of ice cream onto your cone, you need the two sides of your cone to be equal, or your scoop is going to fall out, right? If you tried to put your ice cream in a cone that looked like this, that ice cream's not going to stay. So we need the two sides of the cone to be the same so our scoop will stay in place. So in example 4, these are two tangent lines that meet at this point, so they are the same. So I could set x squared equal to 9. This is going to be an easy peasy one to solve. Take the square root of both sides, but we do have to be careful with our answer because x could be plus or minus 3, right? Negative 3 times negative 3 is 9. 3 times 3 is 9. So here's one for you to try. Pause. Answers are posted online. So example 5 is the ice cream cone problem, but on steroids. We have one scoop of ice cream, but 3 different cones on it. So each cone has to match. So this cone, these two sides should be the same. So if that was 10, that was 10. The two sides of this cone should be the same. If that's 2, that's 2. If this whole side was 8, and I knew that much of it was 2, I could take that away and get 6 here. And now these two cone sides are the same. So now I could either find the whole perimeter, or in this case, they're just asking me to find SR. So SR is from here to here. So that's a total of 16 centimeters. So in try 5, it does want you to find the perimeter of the quadrilateral. Pause. Answers are posted online. A central angle is an angle whose vertex is the center of the circle and the sides are radii of the circle. So this angle here, angle APB, is a central angle because P was the center and AP and BP are radii. And a circle contains 360 degrees. So if I were to draw a whole bunch of central angles in a picture, they would add up to 360. So let's find each central angle in this diagram. Looks like BE and AC are diameters. So that tells us two things. We do have some vertical angles here. So I can say that angle is 63 degrees. We also know that a diameter is a straight line, and straight lines add to 180, right? The linear pair postulate, if two angles are a linear pair, if two angles make a line, they equal 180. So the angle next to the 63 here, because they made this one straight line, would add to 180 with it. So 180 minus 63, I get 117. Same is going to be true on the other side. 63, this angle, and this 90 would have to add to 180 as well. So if I take the 63 plus 90, I get 153. And 180 minus that 153 would be 27 degrees. An arc is the outer curved portion of a circle. And arcs can be measured by the central angle that forms them. So they use a little curve above the letters to show that it's an arc, and we put the little M in front when we're talking about the measure. So this arc here that has endpoints of A and B would be 50 degrees because the central angle ACB was 50 degrees. We can classify our arcs just like we classify angles, right? With angles, we had acute, obtuse, and right. So for arcs, we're going to have minor, major, and semicircle. A minor arc is when it's named by just two letters, and that means it's going to be less than 180 degrees. So when they give us just two letters, they want us to go the shortest way to get from one point to the other. A major arc is three letters, and that's always going to be greater than 180 degrees. So in this case, they showed measure of arc ADB. So they started at A, then they passed through D, and then kept going until they got to B. And that ended up being 310 because we know circles add to 360. So if this was 50, take it away, we got 310. And a semicircle is also three letters, but it's exactly 180. So the endpoints of a semicircle are the diameter. The trickiest thing is because it's doesn't matter which way you would have gone for those two letters. Some people try to write it with two, but technically the only correct way to write our semicircle is with three letters. So we're going to use the diagram from example 6. So I'm going to rewrite my numbers in here. This was 63 degrees, 27 degrees. I'm going to write the 90 and the 117. So arc AB. So the shortest way to get from A to B is this way, and that's 117 degrees. And we know two letters is automatically a minor arc. The next one is ABC. So I want to start at A. I want to hit B first, and then I want to hit C. So together, all this outside, if AC was a diameter, that makes ABC a semicircle and 180 degrees. Let's look at EC. EC, shortest way to get from E to C would be this way. So together, that's 90 and 27, or 117 degrees. And again, two letters is automatically a minor arc. A, B, D. So we're going to go all the way around here. So I could either add together these three arcs or take these two away from 360. To me, I know that ABC is 180, so I'm going to do 180 plus this extra 27, and I get 207. And this one is going to be a major arc because it's more than 180 degrees. It was three letters, and it wasn't a semicircle. Next, we have DB. From D to B, the shortest way would be here. So that's 63 plus 27 together, or 90 degrees. And again, two letters, automatically a minor arc. Now we have EF. B, C. So I have to hit the B before I hit the C. So I'm going all the way around here and then continuing. So again, EB was the diameter, so this half is 180. So 180 plus the 63 is 243. And that's another major arc because it's more than 180. BCE. So we're starting at B, passing through C, ending at E. Since BE was a diameter, that is a semicircle. That's 180 degrees. And our last one is going to be minor because it's only 2 letters, so we know our answer should be less than 180. We're going from A to D. So the shorter way of these two would be going this way, and 90 plus 63 is 153 degrees, minor arc. So for try 7, you're going to do the same thing, find all your central angles, then find the measure of each of the indicated arcs and classify it as minor, major, or semicircle. Pause if you'd like. Answers are posted online, but that is actually the end. So we are done, and that is sections 10.1 and 10.2.